Good morning, dear friends, and I'm Neeraj Gupta. We are having this series of video lectures on measurement and instrumentation subject of electrical and electronics engineering second year. The subject code is KEE302. We start with the philosophy of measurement with the first unit. So, the basic contents which specifically lies in this first unit uh, of this topic is, first of all, what do we understand by the measurements? What is measurements? What is instrumentation? Then second, we will talk about the methods of measurement, instrumentation systems, and measurement system. Then we will talk about the types of measurements, what type of measurements could be done. Then classification of instrument systems. So, as far as concerned with the measurement systems, first of all, we need to understand the concept that what is a measurement. So, measurement of a given quantity is essentially an act of comparison between the quantity whose magnitude is known with the standard one, whose magnitudes we do consider that they are known. Since the two quantities are compared, the result is expressed as a numerical value. So, when we compare two specific quantities, one is known to us, another one is a standard one, that clearly means that the comparison of those will be expressed in the numerical values. So, that is what we call as measurement. Then comes the methods of measurement. Methods of measurements are two specific methods can be described over here. One is direct method and another one is indirect method. So, the direct method says that whatever the quantity is being visible, that is in case of visibility. In direct comparison method of measurement, we compare the quantity directly with the primary or the secondary standard. If we have to measure, for example, if we have to measure the length of a bar, there is a rod or a bar whose length is to be measured. So, what we will do? We will simply put the scale over there and we will measure with the measuring tape or the scale, and the length of that bar which will be marked upon that scale is directly visible to us. There is no other way or another quantity is involved in this, simply the length is being measured. Then comes indirect method. Now, there are so many other quantities which are available which needs to be measured in terms of another quantities. So, numbers of quantity which cannot be measured directly, for example, temperature, for example, pressure. There are so many such quantities which cannot be measured directly. So, the pressure, for instance, we cannot measure the strain in a bar due to the applied force directly. We cannot measure that in a direct way. So, we may have to record the temperatures and pressures of the deep depths of the grounds or in some far off remote places. In such cases, these indirect methods are utilized. So, where the quantity is directly available to us, for example, length, for example, mass, we can directly observe. Level of the liquid, these are directly available. We can measure them directly in terms of length and displacement. But in case of quantities like pressure, force, humidity, temperature, we cannot measure the quantities directly. We have to measure them in terms of some another quantities. So, those methods are called as indirect measurement. Then a generalized instrumentation system, which is also known as instruments and the basic measurement system, that includes the physical quantity which is being measured. It is a measured variable. Then this physical quantity, what is available, is measured in terms of or with the help of sensor, which is also termed as primary sensing element, PSE. This is also called as primary sensing element. Then comes the quantity is being converted from this physical quantity is converted in some another format or some another type of energy with the help of the sensor, which is inputted to this variable conversion element. Now, the type of variable will be changed over here in this variable conversion element. What happens with the variable conversion element? The variable conversion element basically changes the type of variable. For example, if it was a temperature over here, the physical quantity was the temperature. Now, physical quantity was sensed by the sensor. With the help of sensor, it has been converted into some electrical terms. Either it could be a voltage or current, electrical quantity. Because why electrical only? Although the sensors can convert it into some another quantities as well. But why we are talking in terms of electrical? Because we specifically are more capable of measuring the electrical quantities. We do have sufficient methods, sufficient instruments available for measuring the electrical quantities. Plus, we also can convert them into a mechanical also. For example, the pressure can be measured with the help of Bourdon tube. But the fact that why we do not require these mechanical elements or mechanical sensors, the reason is that these includes frictions. The quantities includes friction. So, this particular fact is responsible for basically choosing the electrical quantities. Further from here, there is one another element which is involved over here, which is not marked or given over here. Let me name it here for you. Variable manipulation element. Variable manipulation element basically does it that the quantity which was coming out of this primary sensing element, that was analogous to the physical quantity. That is, either if we were talking about temperature, then in terms of input, what temperature was coming over here, that electrical quantity is being generated. It could be of low amplitude, it could be of very high amplitude, or anyways could comprises of some noise also. So, the sensor has simply given output in terms of the input. The functionality of these variable conversion and variable manipulation elements basically gives the or brings it into a measurable range or makes the signal measurable. As a whole, these two elements, variable conversion and variable manipulation elements, are called as this signal processing, or we also term it as signal conditioning element. The both of the blocks comprises of the signal conditioning block. Out of this block, there could be data transmission element. The functionality of this data transmission element is to transfer the data through a wired channel. It could be wired, it could be wireless, or any means through which the signal could be transmitted, is being provided on a channel and is brought to the data reception element. This is DTE, this is DRE. data reception element. Now, out of this data reception elements, when we are sitting at a remote place, we can use this data reception element as for using it to a remote point. We can store the data, the observer can observe the data, where or it could be presented on a screen. It could be recorded, it could be presented on an element which is also known as data presentation element, and it could be used for actuating the further processes as well. So, there are so many things which can take place, but this is a generalized measurement system. It does not say that every instrument should be comprising the basic order of these aspects like this only. It says it could be having, instrument could be having variable conversion element over here as well. The signal conditioning could be done after that. Data transmission element could be at the first. Multiple variable conversion and variable manipulation element can be available over there. Multiple display recording instruments or actuating instruments could be there. But one thing is sure, that the sensor will be in direct contact with the physical quantity which will be being measured. That is one thing for sure. So, this is about a generalized measurement systems. Remaining, you can go through this slide and can understand. I hope the concept of this generalized measurement system is clear to everyone. Now, we can understand this generalized measurement system with the help of this example of a Bourdon tube. A Bourdon tube is a C-section, kind of a C-section, where this half is fixed and a pressure is being applied from this point. Pressure is being applied from this point. There is an arrangement, this end of the tube is fixed and this free end here, the tip of the Bourdon tube is free to move. Free to move in the sense it could have a deflection in this direction, dx. So, the Bourdon pressure gauge operates on the principle that when pressurized, a flattened tube tends to straighten. That means, if we apply pressure from here, it will try to straighten, tends to straighten or regain its circular form in the cross section. The Bourdon tube comes in a C type, it could be helical type, it could be spiral shaped, although most of the gauges employ the C shape Bourdon tubes, which is type of Bourdon pictured over here. When a gauge is pressurized, the Bourdon creates a dial tip travel to enable pressure measurement. The higher the pressure requirement of the application, the stiffer the Bourdon tube needs to be. The higher the pressure is required, the stiffer the Bourdon tube structure needs to be, which means the Bourdon wall thickness and the diameters are the very key considerations for enabling the required tip travel to traverse through the necessary movement. If this will not be hardened, what will happen? It will easily move down and it will be very difficult to calibrate this on a scale, because here is a scale which this needle is pointing towards. Thus, to facilitate the pressure measurement accuracy, tip travels or traversing of that movement of this tip will be a very important factor. A standard gauge for industrial fluid handling the applications would generally call for an accuracy in ranges of 3 to 5% of the full scale. Now, let me just get this comparison from the generalized measurement system that we have talked about. So, here the primary sensing element is the fixed end of this tube, this particular tubing. This is primary sensing element. Data transmission element, the pressure which is being sensed. Currently, there is no variable conversion taking place. The variable conversion element basically comprises of the free movement of of tip is variable conversion. This is primary sensing. Variable conversion is taking place over here. Further, this linkage, this adjustment link, segment lever, what these things are doing? Data transmission. The data or the displacement is being traveled through with the help of this. Further, this gear system is actually doing variable manipulation, that the gear system is deciding that how much this pointer needs to move. So, this is variable manipulation, and the scale is your data presentation element. Which an observer can directly observe. So, here we can compare that pehle in first case, when the pressure was being applied, the variable which was being changed into the pressure was being converted into the displacement of this free tip. So, it was not an electrical quantity in this case. I hope that make the concept clear about. Now, next we consider the types of instruments. The types of instruments, first one is mechanical instruments. So, initially all the instruments that were available to us for measurements were mechanical in nature. So, mechanical instruments are reliable for static and stable conditions where no vibrations or no dampings are there in the systems. That means the variation are very less. The problem with the mechanical instruments were that these were unable to respond rapidly for measurement of the dynamic and transient conditions, where rapid variations are there in inputs. In those cases, their response time was quite a bit lesser. That means qualitatively. Having moving parts, they are rigid, they are having bulky structures, and are having larger masses. And it is very virtually impossible to do a measurement of a 50 hertz voltage with the help of a mechanical instrument, because this is so fast oscillating, it will be very difficult to measure that particular voltage which is having a frequency of 50 hertz. And these could be a potential source of noise and creating the noise pollutions. While if we compare them with the help with the electrical instruments, it depends on a mechanical meter movement as indicating device. Meter is obviously mechanical over here. Mechanical movements are having some inertias because of the springs, frictions, and various other aspects, and therefore these instruments have a limited time response. Even these were having a limited time response. Time response limited means the response to variation in the input. There, for example, there were electrical recorders which are having a time response of around 0.25 seconds, that is 1/4 of a second, and industrial recorders are having 0.5 to 24 seconds. Further illustrating on types of instruments could be electronic instruments. Electronic instruments, when as we grow on or developed upon these mechanical and electrical instruments, we moved on to electronic instruments. There were a necessity to step up the response time. That means it was required to be improved, and also the detection of the dynamic changes in the certain pressure parameters, which requires monitoring time of the order of milliseconds and many times microseconds. So, the delay between the variation in the input and getting an output from the device should be simultaneous, or of the order of the delay should be of the order of milliseconds and microseconds. So, electronic instruments were using semiconductor devices. The movement involved is that of electrons, which are quite faster. So, response time is extremely small on account of very small inertia of electrons. So, for example of this is CRO, cathode ray oscilloscopes, having a dynamic and transient changes. So, it was having a few nanoseconds response time. These are more reliable. A very weak signal can be detected by using the pre-amplifiers and the amplifiers. The smallest of the signal can be amplified further with the help of the semiconductor chips. Power amplification is a very important when we talk about the bioinstrumentation signals. The signals like ECG, EMG, EEG, these are very weak in nature. The amplitude is very low. For observing them, the power amplification is required. Instrumentation amplifiers are generally being implemented with a very high amplification factors to measure these type of signals, bioinstrumentation signals. There should be ability to obtain indication at a remote location, which helps in monitoring inaccessible or hazardous locations. They are having this ability because interfacing is possible with the help of these electronic instruments. As we can interface, so we can do the remote measurements easily. The detection of magnetically produced signals such as radio, video and microwave signals can be very easily done. The bulkiness of the instruments are gone now because of the size of the chip has gone lower. These are compacts, higher degree of reliability, and their power consumptions are also very low, and especially particularly useful in intermediate signal modifying stages. The signal conditioning circuits in electronic instruments are very powerful. They can bring to the very low amplitude signals into the high ranges and can do the measurements effectively. Then further classification involves of these instruments as absolute and secondary instruments, deflection and null type instruments, analog and digital instruments, and active and passive instruments. So, first we talk about as absolute instruments. Absolute instruments are those instruments which are used to calibrate the further instruments, that instruments which we need to use further. So, these instruments give the value of the electrical quantity in terms of absolute quantities or in terms of some constants of the instruments and their deflections. In this type of instrument, no calibration or comparison with the other instrument is required. They are generally not used in laboratories because these are costlier one. They are mostly used as a means of standard measurements, where the calibration of the instruments are being done and are maintained by the national laboratories and the similar institution of reputations which do these kind of calibrations. Few of the examples of this as absolute instruments are tangent galvanometer, Rayleigh current balance, and absolute electrometer. So, these are few examples of these absolute instruments. With the help of these instruments, further instruments are calibrated. Then comes the secondary instruments. Secondary instruments are direct reading instruments. The quantity to be measured by these instruments can be determined from the deflection of the instrument. As any deflection occurs, with the help of that deflection, directly the quantity can be read out. For example, a voltmeter, a meter, where the deflection of the needle is giving you the value of voltage or currents. They are often calibrated by the comparing with them with some absolute instruments or with the one which are already calibrated. That calibration is also being done with the help of this absolute ones. The deflection obtained with the secondary instruments will be meaningless until and unless these are calibrated. If it is not calibrated, we cannot say we have done the correct measurements. These requires to be calibrated first. These instruments are used in general for all laboratory purposes. Some of the very widely secondary instruments are ammeter, voltmeter, wattmeter, energy meter, ampere hour meters. These are the examples of these secondary instruments. Then there are deflecting type instruments. Deflecting type instruments is another classification of these instruments. In these, the deflection of the instrument basically provides the basis for determining the quantity being measured. For example, if we talk about a PMMC meter, the deflection, PMMC stands for permanent magnet moving coil. The deflection of the moving coil is proportional to the current which is being measured, that is the quantity in the measurement. So, there will be a deflecting torque TD, which is proportional to current, because TD before, as far as concerned with the statement, TD is proportional to I, and here comes TD equal to GI, where G becomes a constant. G is a constant. So, G is basically determined with the help of flux density, number of turns in the coil, then area of the moving coils. These are the few factors which are governing G. So, now if there is a deflecting torque, there should be a controlling torque as well. So, if we say this due to I current, if there comes a deflection of a theta, then there should be a controlling torque which will be stopping this or balancing, counterbalancing this deflecting torque after an angle which is actually showing the current value. So, that comes or that tells to be as or termed as TC, that is TC, and TC is also proportional to the current which is being measured to deflection, that is TC equals to Ki, where K is spring constant. Now, this coil is governed with the help of a spring, that a spring is basically controlling the deflection. So, as there is a deflection, the spring will try to regain its position, and when these two forces or torques will be balanced, at that point the needle will be stopped on a particular point on a scale. When this TC becomes TD, counterbalancing forces are there or counterbalancing torques. So, in this case, if we put the value, we calculate the value I equals to K by G theta. So, that is the concept of this deflecting type instruments. Then comes null type instruments. So, as we have talked about the null type instruments basically requires a null indication. For example, a galvanometer. A galvanometer basically does it what? It tries to find out the null position. So, the scale of the galvanometer is like 0, so this is center point, this is null point. If it is moving in this direction, needle is moving in this direction, the direction of current could be considered right in a circuit, and if it is moving in this direction, the direction of current would be left. So, it also tells the direction of the current and also provides the null position. If it remains on 0, that means no current is flowing through the circuit. So, this 0 or null condition leads to determination of magnitude of measured quantity. For the operation of the null type instruments, the following are required: the effect which is produced by the measured quantity. Similarly, second, the opposing effect whose value is accurately known. Then comes a detector which detects the null condition, that is our galvanometer, and device which indicates 0 deflection when the effect produced by the measured quantity is equal to the effect produced by the opposing quantity. The basic circuit which could be using this null method is a Wheatstone bridge. If this R is changed, to counterbalance this is R1, R2, R3 and R4. So, to counterbalance, if this resistance R1 is being changed to R1 plus delta R, what does this says? That the ratio of arms should be same, that is R1 upon R2 equals to R4 by R3. If it is so, then there will be no current through this branch, or this galvanometer will show 0 deflection. But if this R1 is changed to R1 plus del R, to bring it again to a balance, this R4 is required to be changed to R4 plus delta R, again R1 we can say it as, to maintain that ratio. So, this is an example of null type method. Another example of this could be a DC potentiometer. So, as I have given this, Wheatstone bridge is also dependent or defined with the help of this DC potentiometer also. So, what does it say? This is your known voltage E, this is source battery, rheostat, this is a known voltage which is connected across. So, what happens when comes the null deflection? Where do we find this value of this battery, source battery? This is known to us, this is unknown to us. So, apply switch, when both of the voltages will become equal, then what will happen? This galvanometer will show the 0 deflection. So, the slide wire has been calibrated in terms of EMF with the help of a standard EMF source, that is E1 or E. A null detector is the current whose deflection is proportional to the difference between EMF of the slide, and as soon as these two are equal, there is no current between the or through this galvanometer. When we will be trying to move this wire slide contact on the scale of this wire, what will happen? It will be acting as a circuit. So, when this will be equal, what will happen? There will be no current through the galvanometer and it will show 0 deflection. So, that is what the null condition is. Therefore, the unknown EMF is equal to the EMF across the portion of the slide wire, which is directly indicated by the calibrated scale placed alongside the wire. What will happen? These are the markings on the scale or wire. Per unit resistance of this wire is known to us. So, if this is the length, this multiplied by the per unit length, we can find out the value of the resistance which is required. Then there will be a comparison of null and deflection type instruments. Obviously, null type instruments are comparatively more accurate than in comparison to the deflection type. So, in deflection type, the value of the quantity being measured is displayed in terms of amount of movement of a pointer. The pressure measuring device shown is an example of a deflection type instrument. In previous slides, we have talked about that quadrant tube, that was a deflection type instrument. Alternative type of pressure gauge is the dead weight gauge, which is a null type instrument. Now, dead weight gauge we have not discussed here, but it is an instrument which is of null type for measuring the pressure. Here, the weights are put on top of the piston until and unless the downward force balances the fluid pressure. Weights are added until the piston reaches a bottom level, a known particular specific level, which is known as the null point. And when it reaches the amount of weights that we have put it over there and the cross sectional area, the pressure is calculated. The accuracy of the deflection type pressure measurement instruments depends upon the linearity and calibration of the spring, whilst for the second it relies upon the calibration of the weights. In first case, obviously, spring will be the major contributing factor which will be deciding the accuracy. In second case, the weights that we are putting on the dead weight tester will be deciding the accuracy of the instrument. Further, calibration of these weights are comparatively more easier. So, null type instruments are comparatively considered to be easier to operate. Plus, otherwise also, these instruments are having a bottom line defined. For example, in case of a dead weight test or in case of a galvanometer, a datum line defined. When the pointer is released or pointer is reached to that particular position, the comparison of standard quantity is being done. So, the method is having comparatively more accuracy. While in terms of uses, deflection type instruments are clearly more convenient, because we do not require standard to compare with. So, uses, as far as concerned with the uses, deflection type instruments are good, and as far as concerned with the accuracy, null type instruments are good. A deflection type instrument is therefore done that would be normally used in the workplaces. However, for calibration duties, null type instruments are preferable because of the superior accuracies. Then comes analog and digital instruments. Analog and digital instruments basically are the instruments which will be depending the type of measurement these are being done. The more descriptions regarding this analog and digital instruments will be given in the next lecture. Thank you.